Have you ever noticed that when you unplug your phone, it can still keep charging for a second? Well, that's partially due to something called capacitance. So in this lesson, we're going to break down what that means and how that works in electrical circuits. This is the third lesson in electricity for the general section of your Airframe and Powerplant tests. Click the link in the description below. You can see the written and oral test questions from this material. It merges all of the different questions you'd see in the most popular different study resources out there into one master document. You'd also get access to the 166 other lessons covering each topic for the general section. So let's start with some visuals. A capacitor is actually made up of two different plates that are not touching with an insulating material between them called a dielectric. Now, you can envision a capacitor kind of like a tiny rechargeable tank for electricity. It doesn't make electricity, but it can store it and release it when it's needed. Kind of like a sponge soaking up water, but for electric charge. So now imagine connecting this capacitor to a battery. So one side gets a negative charge and the other side has a positive charge. So now there's current flowing between these two plates. But that current only flows when the capacitor is charging. And once it's fully charged, the current stops flowing between these plates. And that energy stays stored in an electric field between the plates until something gives it a path to discharge. So the capacitor fills up, it holds its charge until it's ready to be released, and then it can be used as needed. And the ability of a capacitor to store its charge is called capacitance. And that's measured in a unit called a farad. But 1 farad is actually huge. So we usually work with smaller units like a microfarad, which is 1/1,000,000th of a farad, or a picofarad, which is 1/1,000,000,000th of a farad. And so now we need to know that there's 3 main things that affect how much energy a capacitor can store. So first, the bigger the plate area, the more room there is to store the charge. Second, the closer those plates are together, the stronger the electric field can be. And third, the type of insulating material, the dielectric used, that also makes a difference. So the schematic symbol that you would see in a wiring diagram is shown like this. So it's like the 2 plates, fairly easy one to remember. And there's actually a formula for this. It's nothing you need to kill yourself to understand right now, but it's worth knowing what each thing stands for in this formula. That's definitely something that comes up quite a bit. So what we have is capacitance equals charge over voltage. So C here equals capacitance measured in farads. Q is charge measured in coulombs. E is the applied voltage measured in volts. Try to remember that one, Q coulombs. So far we've been using a lot of examples with batteries, and we've been talking a lot about direct current up to this point. So what we're going to do is we're going to get into the differences of alternating current and direct current later on. That's lessons 5 and 6. But there are some things that we need to know about how capacitors work in AC versus DC circuits. So first off, DC circuits, capacitors can be used to smooth out small bumps or pulsations in voltage. So when voltage drops slightly, a capacitor can release some of that stored charge and it helps keep things steady. Or if the voltage rises up, it can absorb some of that excess, so it just keeps things nice and even in those DC circuits. In AC circuits, the big thing to know is that there's a voltage rating, and this is the maximum voltage a capacitor can safely handle. So if you apply too much voltage, the dielectric between those plates can break down, causing arcing or short circuit, which can damage the whole entire system. So in AC circuits, the voltage swings up and down more than it would in a DC circuit, so the capacitor needs to be rated to handle more than the average voltage you would expect to see. So the good rule of thumb here for AC circuits, the capacitor's voltage rating should be at least 50% greater than the highest voltage you would expect to see in that circuit. And that's all we have for our lesson on capacitors for today. But unfortunately for this section, there is some math with some figures and equations that you need to know. So you can check out their channel or click the link in the description to get full access to everything, but we'll post it on our channel as well. It's going to be a description of the figures, equations, and how you can actually do the math on this so that you can practice that for your test day.